What is hidden in the Grand Canyon? 13 secrets and wonders. Think the Grand Canyon is just an enormous ditch carved by a river over a very long time? Throw away those simple tourist brochures and basic geology lessons you remember from school. This place is far more than a scenic viewpoint or a hiking destination. It is a living library of our planet's deep past, a natural laboratory that continues to surprise even the most experienced Earth scientists today. In the next few minutes, you are going to discover 13 carefully chosen facts that reveal astonishing layers of history, unexpected life forms, and powerful natural processes still at work right now. Stick with me all the way to the final revelation, because that last secret shows how this one landscape quietly holds answers about changes coming to the entire planet in the centuries ahead. Fact number 1 opens our journey with something most people never stop to consider: the sheer age difference between the rim you stand on and the rock lying far below your feet. Picture yourself standing at the south rim on a clear morning. The sun has just risen, painting the opposite cliffs in warm gold and deep rust. You look down, and down, and down. The drop reaches almost 1 mile straight to the river. What many visitors do not realize is that the rock you are standing on formed roughly 270 million years ago, while the dark, ancient layer touching the river is close to 1,800,000,000 years old. That gap, more than 1.5 billion years, is not a gentle transition. It is one of the most dramatic breaks in the rock record found anywhere on Earth. Geologists call this enormous time gap the Great Unconformity. Imagine opening a thick history book only to find that hundreds of pages have been ripped out, leaving nothing but a sharp, flat cut between what came before and what came after. That is exactly what happened here. For an incredibly long stretch of time, hundreds of millions of years, this region was exposed at the surface, weathered and eroded so deeply that vast thicknesses of rock simply vanished. Later, the land slowly sank, ancient seas returned, and new layers began piling on top of the worn-down surface like fresh pages glued over the missing chapters. Why does this matter so much? Because that missing time is not a small detail. It represents an immense chapter of Earth's story that scientists are still piecing together from clues found in other parts of the world. Some researchers estimate that up to 1 billion years of sedimentary layers were removed here. Layers that, in other continents, still preserve records of early complex life, massive climate swings, and the slow assembly of ancient supercontinents. In the Grand Canyon, those pages are gone, scrubbed away by wind, rain, ice, and rivers, long before the first dinosaurs appeared. Walk along any trail that descends into the canyon, and you can actually touch this break with your own hands. Near the bottom of the inner gorge, the Vishnu schist and Zoroaster granite sit directly beneath much younger Tapeats sandstone. The contact is razor sharp. No gradual mixing, no transitional soils, just hard, ancient basement rock against beach sand deposited 500 million years later. Stand there and run your fingers along that line. You are literally feeling a billion-year jump in Earth's diary. Modern studies using advanced dating techniques, including uranium-lead zircon analysis and thermochronology, have helped pin down when this great erosion happened. Most evidence now points to several major pulses between roughly 1.2 billion and 700 million years ago, with the final major stripping occurring just before the Cambrian seas flooded back in around 540 million years ago. Those dates come from painstaking work published in journals such as Geology and Nature Geoscience over the past 2 decades. But the story gets even more interesting when you realize this unconformity is not unique to the Grand Canyon. Versions of it appear across much of North America. In some places, the gap is smaller. In others, it is even larger. Yet nowhere else can you see such a clean, dramatic expression of it over such a huge vertical distance in one continuous view. That is why this landscape has become one of the most important natural classrooms on the planet for understanding how continents grow, how supercontinents break apart, and how long periods of stability can be followed by sudden, continent-scale erosion. Now think about what it means for us today. The same forces that erased those ancient layers are still active, just much slower. Rain, freeze-thaw cycles, and the patient work of the Colorado River continue to sculpt the canyon at rates measured in fractions of an inch per century. Every rockfall you hear echoing off the walls is a tiny continuation of the same process that created the Great Unconformity long ago. The canyon is not finished. It is still writing its own next chapter, one grain of sand at a time. So when you stand at the rim and gaze into that immense space, remember you are not just looking at beautiful scenery. You are looking across an unimaginable stretch of missing time, a reminder that Earth's history is full of gaps, erasures, and quiet rebirths. And that single thought sets the stage for everything else we are about to uncover. We step away from that billion-year scar and move towards something equally surprising. The way the canyon's rock layers tell a story of oceans rising and falling, mountains being born and worn flat, all preserved like snapshots in stone. Fact number 2 takes us right into the heart of what makes this place feel like a time machine. The stacked rock layers themselves, each one a frozen snapshot of a completely different world that once covered this exact spot. Imagine hiking down one of the steep trails from the rim, maybe Bright Angel or South Kaibab. With every switchback, you drop deeper, the colors shift, the textures change, and the air gets warmer. What started as pale limestone at the top slowly gives way to rusty reds, soft grays, bold whites, and finally the dark, ancient basement far below. These are not random colors or accidents of lighting. They are deliberate records, page after page in a massive book that Earth wrote over hundreds of millions of years. Scientists divide the main visible layers into 3 big packages. At the very bottom, you find the Vishnu basement rocks, mostly dark schist and granite that formed between about 1.84 billion and 1.7 billion years ago. These started as sediments and volcanic material in a long-gone ocean basin. Intense heat and pressure from colliding landmasses turned them into the tough, folded, metamorphic rocks we see today, with shiny mica flakes that catch the light like tiny mirrors. Right above that ancient foundation sits the tilted Grand Canyon supergroup, a series of sedimentary and volcanic layers deposited roughly between 1.25 billion and 729 million years ago. These rocks tell a story of ancient basins, rivers, tidal flats, and shallow seas during a time when single-celled life was just beginning to leave traces, like stromatolites in some of the formations. The layers here are tilted at steep angles because tectonic forces folded and faulted them before the next big chapter began. Then comes the most famous stack, the flat-lying Paleozoic strata that form the classic stepped cliffs and slopes everyone pictures when they think of the Grand Canyon. These layers pile up from about 530 million years ago down to 270 million years ago, recording a long sequence of rising and falling seas along the edge of the ancient supercontinent. Starting from the bottom of this Paleozoic package and working up, the Tapete sandstone rests directly on the older rocks after that huge time gap we talked about last time. This coarse, beach-like sandstone formed around 525 to 510 million years ago as a shallow sea advanced over the eroded landscape, depositing sand grains worn from distant mountains. Above it lies the Bright Angel Shale, a soft, greenish-gray mud rock full of trilobite fossils that shows the sea deepened into calmer waters where fine silt settled slowly. It dates to roughly 515 to 505 million years ago. Next up is the Muav limestone, thinner and more variable, but still marine, with fossils indicating shallow, warm waters around 500 million to 495 million years ago. Then the massive Redwall limestone rises as one of the most striking cliffs. Thick, sheer walls of gray limestone, often stained red from iron oxides leaking down from layers above. Formed in a clear, shallow tropical sea about 340 to 330 million years ago, it holds brachiopods, corals, and crinoid fossils that prove this region was once far closer to the equator. The Supai group follows, a mix of sandstones, shales, and limestones, deposited in coastal plains, river deltas, and tidal flats between about 320 and 290 million years ago. These layers show repeating cycles of sea level change, with red hues from iron-rich sediments. The Hermit Shale comes next, brilliant red slopes of fine mudstone from around 290 to 280 million years ago, laid down in swampy lowlands where ferns and early land plants left impressions. Then the dramatic Coconino Sandstone, bright white to buff cross-bedded dunes that scream ancient desert. Windblown sands piled up in massive dunes about 280 to 275 million years ago, with fossilized trackways of scorpions, millipedes, and small reptiles preserved on the sloping surfaces. The Toroweap Formation sits above that, a mix of sandstone, gypsum, and limestone from roughly 275 million years ago, recording a return to shallow marine and coastal environments with evaporite minerals showing drier conditions. Finally, capping everything, the Kaibab Limestone, the pale, fossil-rich layer that forms the rim today. Deposited in a warm, shallow sea around 270 million years ago, during the early to middle Permian, it contains brachiopods, sponges, and bryozoans, marking the last major marine incursion before the region became mostly dry land. Each of these layers tells its own vivid story. One moment this place was a sandy beach with crashing waves. The next, it was a vast desert with wind-sculpted dunes taller than many modern buildings. Then, a quiet lagoon where lime mud accumulated. Later, a swampy floodplain with early forests. Sea levels rose and fell multiple times, driven by global climate shifts, continental drift, and ice ages far away. The fossils inside, from simple marine invertebrates to tracks of early land animals, show life evolving right alongside these changing environments. What makes this sequence so special is how cleanly preserved and continuously exposed it is. Few places on Earth let you walk through such a complete vertical slice of nearly 260 million years of sedimentary history in one continuous view. Researchers from universities and the United States Geological Survey have studied these layers for over a century, using radiometric dating, fossil correlations, and detailed mapping to build an incredibly accurate timeline. Stand at any overlook and trace your eye down the walls. You are literally scanning backward through deep time. The white kaibab at the top was once seafloor, teeming with creatures similar to those in modern coral reefs. Drop lower to the red supai and hermit slopes, ancient river deltas and coastal swamps. Reach the white Coconino Dunes, a scorching Permian desert. Keep going past the massive red wall cliffs to the Tapeats beach sands, then across that billion-year jump to the dark Vishnu rocks, born in volcanic island collisions long before complex animals existed. This layered record is not static. Erosion continues to reveal more details every year. Rockfalls expose fresh surfaces, rain carves new gullies, and the river below keeps widening the canyon. Every visit shows slightly different views of the same ancient story. So the next time someone calls this just a big hole, smile quietly. What you are seeing is one of the planet's most complete geologic diaries, a place where Earth kept meticulous notes on oceans, deserts, mountains, and the slow march of life itself. We leave these stacked pages of stone and turn towards something that brings those ancient environments to life in a whole new way. The surprising plants that somehow still thrive in this extreme vertical world of rock and sun. Fact number 3 brings us to one of the most surprising things about this giant chasm. Even though it looks like one massive, uniform landscape from the rim, the temperature, rainfall, and growing conditions change so dramatically from top to bottom that it is like walking through 5 completely different climate zones in the space of a single mile of elevation. Stand at the south rim in summer. The air is dry, the sun beats down hard, and daytime highs regularly climb into the 90s or even low 100s Fahrenheit. Pinyon pines, junipers, and sagebrush dominate the scene, classic high desert plants that can handle long droughts and freezing winters. Annual precipitation here averages only about 15 inches, most of it falling as winter snow or summer thunderstorms that arrive fast and leave just as quickly. Now imagine dropping down the trail about 2,000 feet. You enter what botanists call the transition zone. The pinyon juniper forest gives way to denser stands of ponderosa pine, taller trees with thick, cinnamon-colored bark that smell like vanilla when the sun warms them. Temperatures cool noticeably. You might lose 10 to 15 degrees just from the elevation gain in reverse. Rainfall increases a bit too, maybe up to 20 inches a year, enough to support thicker undergrowth and occasional wildflower blooms after monsoon rains. Keep descending another 2,000 feet or so, and you reach the canyon's inner subtropical belt. Here, the dominant trees are Utah agave, yucca, and scattered gamble oak, mixed with occasional Douglas fir in shaded north-facing slopes. Daytime heat builds intensely in summer, often well over 100 degrees Fahrenheit at the river level, while nights can still drop into the 40s. Precipitation remains low, around 8 to 12 inches annually, but the intense sun and heat create a microclimate that feels almost desert-like, despite the surrounding rock walls trapping warmth. Finally, right along the Colorado River itself, conditions shift again. The narrow inner gorge acts like a natural oven in summer, with temperatures sometimes hitting 120 degrees Fahrenheit or more. Yet because the river provides constant moisture, and the steep walls create pockets of shade, certain plants that would never survive on the rims thrive down here. Fremont cottonwoods with their shimmering leaves, coyote willows, cattails in backwater marshes, and even small stands of emery oak and Arizona walnut in protected side canyons. Winter lows at river level rarely dip below freezing for long, so some plants keep green year-round. This vertical stacking of climates happens because of something called elevational zonation. For every 1,000 feet you descend in the Grand Canyon, average temperature rises roughly 3 to 5 degrees Fahrenheit, the opposite of what happens when you climb a mountain. Combine that rapid temperature gradient with dramatic changes in solar exposure, wind patterns, and soil moisture, and you end up with 5 distinct life zones packed into one relatively small vertical distance. The cold, dry upper Sonoran zone at the rims with pinyon juniper woodland. The warmer, slightly wetter transition zone with ponderosa pine forests. The hot, arid lower Sonoran zone covering most of the inner canyon walls. Narrow riparian corridors hugging the river with lush, water-dependent vegetation. Isolated hanging gardens in seeps and springs where ferns, orchids, and mosses grow on dripping limestone walls. Scientists have documented more than 1,700 plant species in the park, with roughly 10% found nowhere else on Earth. Many of these endemics, plants that live only here, owe their existence to these sharp climate contrasts. Take the century milkvetch, for example, a tiny purple-flowered legume restricted to specific limestone outcrops in the inner canyon, where winter freezes are rare and summer heat is intense, but brief enough for it to complete its life cycle. Or consider the California condor's favorite snack plants, agaves and yuccas, which bloom spectacularly in the lower elevations, providing nectar and pollen when higher zones are still dormant. The vertical migration of pollinators, birds, and insects follows these blooming waves up and down the canyon walls with the seasons, creating one of the most dynamic biological calendars anywhere in North America. What is really remarkable is how these climate zones influence each other. Summer thunderstorms that soak the rim often produce flash floods that race down side canyons, carrying seeds, nutrients, and sediment all the way to the river. Winter snowmelt from the high plateaus feeds springs that emerge hundreds of feet below the rim, creating those hanging gardens that look almost impossibly green against red rock. The entire system is connected. Change the rainfall pattern on the Kaibab Plateau, and you eventually affect plant communities along the Colorado River more than a vertical mile below. Researchers from the United States Geological Survey, National Park Service, and universities have been monitoring these zones for decades using weather stations placed at different elevations, remote sensing data from satellites, and long-term vegetation plots. Studies published in journals like Ecological Applications show that the canyon's elevational gradient makes it an exceptionally sensitive indicator of climate change. As average temperatures rise across the Southwest, plant communities are already shifting upward. Ponderosa pines creeping higher on the rims, drought-tolerant species expanding downward into areas that used to be too hot and dry even for them. Think about standing at an overlook on a hot July afternoon. You feel the dry heat on your skin, see the shimmer of distant cliffs, watch a raven ride thermals rising off the canyon floor. What looks like one landscape is actually a vertical stack of 5 separate worlds, each with its own temperature regime, rainfall amount, dominant plants, and seasonal rhythm. That single mile of drop creates more biological variety than you would find crossing hundreds of miles of flat land in many other parts of the country. This vertical climate sandwich is one of the main reasons the Grand Canyon supports such an astonishing range of life, and why small changes at the top can ripple all the way to the bottom over time. We step out of these layered climate worlds and move toward the animals that have learned to live inside them. Creatures so perfectly tuned to this extreme vertical puzzle that many exist nowhere else on the planet. Fact number 4 pulls us into the quiet, stubborn survivors that somehow manage to call this vertical desert home. The plants that have evolved extraordinary tricks to live where most greenery would give up within days. You drop below the rim, and the first thing that hits you is how sparse everything looks. Bare rock everywhere, scorching sun, thin soil pockets clinging to ledges. Yet, scattered across those impossible slopes, you spot bursts of life that refuse to play by normal rules. Plants that look tough, spiky, silvery, or strangely delicate, each one a masterclass in beating extreme conditions. Start with the most iconic resident of the lower canyon walls, the agave. Not just any agave, several species thrive here, but the Utah agave stands out as a real survivor. Picture a rosette of thick blue-gray leaves edged with sharp black teeth, sometimes reaching 3 feet across. It sits on a narrow ledge hundreds of feet above the river, roots wedged into tiny cracks where rainwater barely collects. For most of its life, anywhere from 10 to 30 years, it stores water like a living tank, grows slowly, and waits. Then, in one dramatic final act, it sends up a flowering stalk that can tower 15 to 20 feet high, packed with hundreds of yellow tubular blooms that attract bats, hummingbirds, and bees from miles around. After that single massive effort, the plant dies, but it leaves behind dozens of pups, clones that sprout from the base and start the cycle again. Scientists who study desert succulents say this boom and bust strategy is perfectly tuned to the canyon's unpredictable rainfall. Store for decades, reproduce explosively when conditions allow, then let the next generation carry on. Move a little higher and you find yuccas, especially the banana yucca and Mojave yucca, standing like sentinels on sunny slopes. Their sword-shaped leaves are coated in a waxy cuticle that cuts water loss to almost nothing, and long taproots plunge deep into fractures, searching for hidden moisture. The flowers are creamy white bells that open at night to draw in yucca moths, the only insects that can pollinate them. The moth lays eggs inside the flower. The larvae eat a few seeds but leave most for the plant to reproduce. It is one of the tightest partnerships in nature. The plant depends completely on the moth, and the moth depends completely on the plant. Remove one, and the other disappears. Studies from the last 20 years show these mutualisms are holding strong in the Grand Canyon, even as surrounding deserts face more drought stress. Then there are the hanging gardens, small green miracles tucked into seeps where groundwater trickles out of the rock. These are the places where maidenhair ferns drape like lace curtains over dripping limestone, where crimson monkeyflower glows against wet cliffs, and where tiny orchids hide in mossy pockets. The constant moisture creates a pocket of humidity that can be 20 to 30% higher than the surrounding air, letting plants more typical of higher, wetter elevations survive hundreds of feet below their normal range. Researchers have counted more than 200 species in these isolated oases, including several rare endemics found nowhere else. One favorite is the alcove bog orchid, small, delicate, and perfectly at home on dripping walls where almost nothing else grows. Higher still, in the transition zone, you meet the pinyon pine and Utah juniper, working together in what ecologists call a woodland mosaic. The pinyon produces nutrient-rich nuts every few years in bumper crops that feed everything from rodents to people. Native tribes have harvested them here for centuries. The trees themselves are drought deciduous in the worst years. They drop needles to reduce water loss, looking half dead until rain returns. Junipers, meanwhile, have scale-like leaves that lose almost no moisture, and roots that spread wide and shallow to catch every drop. Together they create microclimates under their canopies, shade, trapped leaf litter, cooler soil, that allow grasses, wildflowers, and even small shrubs to grow in places that would otherwise be barren. What ties all these plants together is adaptation pushed to the limit. Many have silvery or gray foliage to reflect intense sunlight and reduce heat buildup. Thick cuticles, sunken stomata, and cam photosynthesis, a special way of taking in carbon dioxide at night when it is cooler and less water evaporates, let them photosynthesize with far less water than ordinary plants. Some, like certain cacti and milk vetches, go dormant for years, waiting out long dry spells as seeds or shriveled stems until the next good monsoon. Scientists from the National Park Service and partnering universities have been tracking these species for decades through permanent plots and remote cameras. Data from the early 2000s through the mid-2020s show that many canyon plants are remarkably resilient so far. They have dealt with dry spells for millions of years. But rising temperatures and shifting precipitation patterns are starting to push some to their edges. Pinyon pines, for instance, have suffered widespread die-offs in other parts of the Southwest during extreme droughts, and the canyon's populations are being watched closely as an early warning system for broader ecosystem stress. Stand on a trail and look across at a sheer red wall dotted with agaves, yuccas, and the occasional bright green seep. What seems like empty rock is actually a carefully tuned community of specialists, each plant solving the same brutal equation of heat, aridity, and thin soil in its own ingenious way. They do not just survive, they turn impossible places into living landscapes. That quiet determination sets the stage for the animals that move among these plants, creatures that have taken adaptation even further, turning the canyon's vertical extremes into their personal advantage. Fact number 5 brings the canyon's wildlife into sharp focus. Animals that have turned this steep, sun-blasted, water-scarce vertical world into a surprisingly rich home, with several species found nowhere else on Earth. You hike down into the inner canyon on a hot afternoon, and the silence feels almost heavy, until a small gray shape darts across the trail. It is a rock squirrel, but not the plump backyard kind you see at higher elevations. This one has longer legs, a bushier tail, and moves with quick, deliberate hops, suited to scrambling over boulders and leaping between narrow ledges. It pauses, stands upright on its hind legs like a tiny sentinel, and watches you with bright black eyes before vanishing into a crack. These squirrels are canyon specialists. They drink almost no free water, getting most of their moisture from cactus pads, seeds, and the occasional green shoot. Their kidneys are extra efficient at concentrating urine, a tiny but critical adaptation that lets them live in places where rain might not fall for months. Lower still, near the river, you hear a sharp, rasping call that echoes off the walls. Look up and you might spot a California condor soaring on 10-foot wings, one of the rarest birds in North America and a true canyon resident. By the early 1980s, only 22 condors remained in the wild, all in California. Through intensive captive breeding and careful releases, the population has slowly climbed back to more than 500 birds today, with a growing number using the Grand Canyon as a core part of their range. They ride the powerful thermals rising off the hot inner gorge, scanning for carcasses of bighorn sheep, deer, or elk that have fallen or died naturally on the cliffs. Their bald heads help prevent bacterial buildup when they feed inside carcasses, and their slow metabolism lets them go days between meals. Park biologists track them with satellite tags and report that the canyon's remote ledges provide some of the safest nesting sites left for the species. Steep, inaccessible cliffs that keep most predators away. One of the canyon's most charming endemics is the humpback chub, a silvery, large-finned fish found only in the Colorado River and a few of its major tributaries. Adults reach about 20 inches long, with a pronounced hump behind the head that gives them their name. That hump is not decorative. It is packed with fat reserves that help the fish survive long periods of low food and extreme temperature swings in the river's naturally fluctuating flows. Before dams changed the river, spring floods scoured spawning gravel and kept water cold and silty, perfect conditions for humpback chub eggs and fry. Today, with clearer, steadier water from upstream reservoirs, populations have declined sharply. But recovery efforts, including controlled high-flow experiments from Glen Canyon Dam, have helped stabilize numbers in the Grand Canyon Reach. Researchers estimate several thousand adults still live here, making this one of the last strongholds for the species. Then there are the bighorn sheep, the icons of the canyon walls. These muscular animals with massive curved horns can weigh up to 300 pounds, yet they move across near vertical rock faces with astonishing ease. Specially adapted hooves with rough, rubbery soles and hard outer edges act like natural climbing shoes, gripping tiny ledges and cracks. They can jump 6 feet straight up and land precisely on a 6-inch shelf. Water is their biggest challenge. They can go weeks without drinking by getting moisture from plants and licking dew or seeps. But they still need to reach known springs or the river every few weeks in summer. Herds of 30 to 50 animals roam the inner canyon, using narrow trails humans can barely follow. Population surveys from the National Park Service show numbers holding steady at around 500 animals, thanks in part to the canyon's isolation from diseases carried by domestic sheep. In the riparian zones along the river, you find ringtail cats, small, fox-like carnivores with enormous eyes and banded tails longer than their bodies. They are strictly nocturnal, using those huge eyes and sensitive whiskers to hunt mice, lizards, insects, and fruit in pitch darkness. Their hind feet can rotate 180 degrees, letting them descend head-first down tree trunks or sheer rock, a trick that helps them escape predators and reach hidden food caches. Ringtails are so common along the river corridor that rangers joke they are the canyon's unofficial night watchmen. And do not overlook the tiny but remarkable creatures. Side-blotched lizards that change color slightly with temperature. Canyon tree frogs that call only after rare rains. And tarantula hawks, massive wasps whose sting is among the most painful known to science, yet used only for paralyzing spiders to feed their larvae. Each species has carved out its precise niche in the canyon's layered climates. What unites these animals is specialization pushed to an extreme. Many have higher water conservation abilities, better heat tolerance, or more efficient movement than their relatives living on flat land. Long-term monitoring by park scientists and university teams shows that while some populations face pressure from changing river flows, invasive plants, or warming temperatures, the canyon's vertical complexity still offers refuges: cool, shaded slots, perennial seeps, isolated ledges that help buffer against broader regional stress. Watch a bighorn sheep pick its way along a cliff hundreds of feet above you, or listen to a condor's low grunt as it circles overhead, and you realize these creatures are not just surviving in the Grand Canyon. They are thriving in a place that would defeat almost any other animal. Their adaptations are living proof of how much evolutionary creativity can emerge when life is forced to solve the same harsh puzzle in endlessly different ways. That ingenuity leads us naturally to the next layer of the story: the ancient remains preserved in the rock itself. Fossils that show us what lived here long before any of today's animals appeared. Fact number 6 takes us deeper into the stone itself. the ancient fossils locked inside the canyon walls that quietly document more than 500 million years of life on this planet, from simple ocean dwellers to the first footsteps of creatures that left the sea behind. You pause on a narrow ledge halfway down a trail and notice small, perfectly round impressions in the gray limestone under your boots. They look almost like coins pressed into wet clay long ago. Run your finger over one and feel the faint ridges. These are crinoid stem pieces, the segmented stalks of sea lilies that once swayed in warm, shallow Permian waters about 270 million years ago. When the animal died, its calcareous plates scattered across the seafloor, got buried in lime mud, and hardened into rock. Millions of years later, erosion cut the canyon open and exposed them again for anyone willing to look closely. Walk a little farther and you find larger treasures. Brachiopod shells, two-valved creatures that look superficially like clams, but belong to an entirely different branch of the animal kingdom. Their shells often show delicate ribbing or folds that record how water currents flowed around them as they filtered food. In the Kaibab limestone at the rim and the Redwall limestone farther down, thousands of these shells appear in dense layers called coquinas, ancient shell graveyards where storms or changing currents swept them together and buried them quickly. Paleontologists who have studied these beds estimate that some layers contain millions of individual brachiopods per cubic meter, giving us a snapshot of thriving seafloor communities just before the biggest mass extinction in Earth's history wiped out more than 90% of marine species at the end of the Permian. Drop lower into the Muave and Bright Angel formations, and the fossils change character. Here you start seeing trilobites, those iconic segmented arthropods with compound eyes made of hundreds of tiny lenses. Some species in the canyon reach only half an inch long. Others stretch to 4 or 5 inches. Their calcite exoskeletons preserve beautifully because the mud they lived in was fine and oxygen-poor, slowing decay. One particularly well-known form from the Bright Angel Shale is Elrathia kingi, a smooth, oval trilobite whose fossils are so abundant that collectors have nicknamed them canyon pennies. When alive, these animals crawled across muddy seafloors, scooping organic particles, much like modern sand dollars do today. Their presence tells us the Cambrian seas here were calm and nutrient-rich, supporting diverse bottom-dwelling communities around 510 million years ago. Even older traces appear in the Tapete sandstone right above the Great Unconformity. Look carefully at bedding surfaces and you might spot small, winding trails and burrows, trace fossils left by worm-like organisms tunneling through wet sand on an ancient beach. These simple markings, called Scolithos and Cruziana, are among the earliest signs of animal behavior we can see in the canyon. They date to the very beginning of the Cambrian explosion, when complex multicellular life suddenly diversified after billions of years of mostly microscopic organisms. No actual body fossils survive in these coarse sands, but the traces prove that something was actively moving, feeding, and hiding on that prehistoric shoreline. Higher up in the Coconino Sandstone, you encounter something completely different. Fossilized trackways preserved on the sloping surfaces of ancient dunes. These are footprints. Small, three-toed impressions from early reptiles, larger, four-toed prints from amphibians, and delicate trails left by scorpions and millipedes. The tracks slope consistently in one direction, because the animals were walking up the windward side of moving sand dunes about 280 million years ago. Some trails show where a millipede paused, turned, and continued. A brief moment of indecision, frozen in time. Researchers have identified more than 20 different kinds of vertebrate tracks in these layers, offering rare glimpses into dry land life during the early Permian, when this region was a vast coastal desert. What makes the Grand Canyon's fossil record so valuable is the vertical stacking and excellent exposure. You can literally walk through time, seeing how marine communities evolved from simple burrowers in the Cambrian, through diverse filter feeders in the Devonian and Mississippian, to early land colonizers in the Permian, all in one continuous outcrop. No other single location on Earth preserves such a long, unbroken sequence of Paleozoic life with this level of clarity and accessibility. Scientists from the Smithsonian, University Geology departments, and the National Park Service have cataloged thousands of specimens over the past century. Many key studies, published in journals such as Paleobiology and the Journal of Paleontology, rely on canyon material to define species, understand extinction patterns, and reconstruct ancient environments. The fossils are protected by federal law inside the park, but careful documentation and casts allow researchers worldwide to study them without removing originals. Stand next to a layer studded with brachiopods or trilobites, and you realize you are touching direct evidence of worlds that vanished long before dinosaurs existed. These small, silent remnants show how life persisted through rising seas, falling seas, massive volcanic episodes, and at least 2 major extinction events. They remind us that the canyon is not just rock. It is a cemetery, a nursery, and an archive all at once, holding stories of survival and change that stretch back 500 million years. That deep time menagerie preserved in stone naturally leads us to the next chapter, the traces left by the first humans who walked these same trails, lived in these same cliffs, and left their own quiet marks on the landscape. Fact number 7 shifts our gaze from ancient seas and desert dunes to the people who first walked these same cliffs thousands of years ago. The early inhabitants whose tools, shelters, seeds, and footprints still lie quietly in protected alcoves and dry caves throughout the canyon. Imagine standing inside a shallow overhang, high on a north-facing wall, the afternoon light slanting in just right. The floor is covered in fine dust that has not been disturbed in centuries. In one corner, you see small blackened patches on the rock, fire hearths used again and again. Nearby lie fragments of split twig figurines, delicate animal shapes made from split willow twigs, twisted and bound into the rough outline of a bighorn sheep or deer. These little sculptures, some only a few inches long, date back more than 4,000 years. Archaeologists believe they were created as part of hunting rituals or ceremonies, perhaps carried for luck or placed in sacred spots. Hundreds have been found in dry caves across the region, perfectly preserved because the arid conditions prevented decay. No one knows exactly what they meant to the people who made them, but their careful craftsmanship shows deep respect for the animals they hunted. Lower down, in larger alcoves that catch morning sun, you find evidence of more permanent life. Circular stone rings mark the foundations of small houses built from local limestone and sandstone slabs. Some structures still have intact roofs of juniper poles and thatch, sealed with mud. Inside, archaeologists have uncovered grinding stones worn smooth from years of processing corn, beans, and squash. Stone projectile points chipped to razor sharpness. Bone awls for piercing leather, and baskets woven so tightly they still hold shape after more than 1,000 years. These sites belong to ancestral Puebloan farmers who lived here between roughly 1,300 and 800 years ago. They planted crops in side canyons where springs provided reliable water, built check dams to slow runoff and capture soil, and stored surplus food in sealed jars buried in cool alcoves. One of the most striking discoveries comes from caves used as storage or burial places. In some locations, preserved human remains wrapped in finely woven textiles have been found alongside offerings of turquoise beads, shell jewelry brought from distant coasts, and macaw feathers traded from what is now northern Mexico. Radiocarbon dating places these burials between about 1,000 and 700 years ago. The textiles themselves are extraordinary. Cotton cloth dyed with plant pigments in red, blue, and yellow, woven on simple looms with intricate patterns that show knowledge passed down through generations. Even earlier traces appear in the form of pictographs and petroglyphs pecked or painted on canyon walls. High above the river, protected under overhangs, you see handprints outlined in red ochre, zigzag lines representing lightning or serpents, bighorn sheep with exaggerated curved horns, and human figures wearing elaborate headdresses. Some panels date to the Archaic period more than 3,000 years ago. others to the later basket maker and Pueblo eras. The images are not random. Many cluster near water sources or hunting grounds, suggesting they marked important places or told stories about seasonal movements, successful hunts, or spiritual events. What ties all these remains together is careful adaptation to a harsh but resource-rich environment. The people here were not isolated. Trade networks stretched hundreds of miles. They exchanged turquoise, shells, feathers, and pottery for corn from farming communities to the south and east, obsidian from volcanic regions far to the north, and salt from distant playas. They timed their movements with the seasons. Higher elevations in summer for hunting deer and gathering piñon nuts, lower canyons in winter for milder temperatures and access to the river. Modern archaeological work, carried out with deep respect for descendant communities, relies on non-invasive techniques whenever possible. Ground-penetrating radar to locate buried structures without digging, LiDAR scans from drones to map hidden alcoves, and careful surface collection of artifacts exposed by erosion. Teams from the National Park Service, universities, and tribal partners have documented more than 4,000 archaeological sites within the park boundaries. Many remain unexcavated, to preserve them for future study and out of respect for cultural significance. These early inhabitants left no written records, but the physical traces speak clearly. Small family groups, skilled hunters and gatherers who later became farmers, builders who worked with the canyon's natural architecture, artists who told stories on stone, and people who maintained connections across vast distances. Their presence shows that humans have been part of this landscape for at least 12,000 years, from the earliest big-game hunters who followed mammoths and ground sloths through the region at the end of the Ice Age, to the farmers who transformed side canyons into productive gardens. Stand in one of those quiet alcoves today and listen to the wind moving through the canyon. The same wind that carried pollen to ancient fields now moves dust across the same stone floors. The hearths are cold, the baskets brittle, the figurines fragile. Yet they remain because the canyon's dry climate and protected locations acted like natural museums. Every split twig animal, every worn mano and matate, every faded handprint is a direct link to minds that once looked at these same cliffs and saw a possibility. Their story reminds us that the Grand Canyon has always been more than scenery. It has been home, refuge, sacred ground, and classroom for people who learned its rhythms intimately and passed that knowledge forward. That long human thread woven into the canyon's fabric naturally brings us to the next surprising element: the volcanic forces that erupted right in the middle of this ancient landscape and left their own dramatic marks on the scenery. Fact number 8 reveals a side of the Grand Canyon most visitors never expect to see: the dramatic black scars and frozen rivers of lava that erupted right in the middle of this ancient landscape and reshaped entire sections of the canyon floor in spectacular fashion. Picture yourself floating down the Colorado River on a calm stretch between River Mile 90 and 110. The walls rise steep and red around you, then suddenly you round a bend and everything changes. Towering dark columns of basalt rise straight out of the water on both sides, massive vertical pillars that look almost too perfect to be natural. These are the remnants of ancient lava dams, some reaching more than 2,000 feet above the present river level. They are not small flows. They are colossal volcanic events that repeatedly blocked the entire canyon, turned the river into a series of huge temporary lakes, and left behind some of the most striking volcanic features found anywhere in North America. These eruptions happened relatively recently in geologic terms, mostly between about 725,000 and 100,000 years ago, with the most active period concentrated between 725,000 and 475,000 years ago. The source was a series of small volcanic vents and fissures located on the north side of the canyon, particularly in the Uinkaret volcanic field just west of the park. Lava poured over the rim in enormous sheets, cascaded down the steep walls and glowing rivers hundreds of feet wide, and reached the Colorado River in massive, fast-moving fronts. When that molten rock hit the cold water, the outer layers chilled instantly into glassy black crust, while the interior stayed hot for months or even years, creating the thick, columnar jointing you see today, those perfect hexagonal pillars that look like they were carved by giants. The biggest of these lava dams, and one of the most studied, is the one that formed at Toro Weep Overlook near River Mile 179. At its maximum, this single dam was more than 600 feet thick at the base and backed up the river into a lake that stretched more than 100 miles upstream, flooding parts of what are now Marble Canyon and the Upper Grand Canyon. Water eventually overtopped the dam, but not before carving a new, narrower channel through the basalt. In other places, multiple flows stacked on top of each other, creating layered dams more than 1,000 feet high. Radiometric dating of the basalts using argon-argon and uranium-thorium methods has given scientists a remarkably detailed timeline of these events, published in journals such as Quaternary Research and Geosphere over the past 25 years. What makes these lava dams especially fascinating is what happened after they formed. When the river was blocked, fine sediment settled out in the quiet lake waters behind the dam, creating thick layers of lake sediment, light-colored silt and clay that contrast sharply with the dark basalt. In some places, these lake beds are still visible as flat benches high above the modern river. When the dams eventually failed, sometimes catastrophically as water pressure eroded the weaker edges, huge floods roared downstream, carrying basalt boulders the size of houses and reshaping the river channel in dramatic ways. Evidence of these outburst floods appears in giant ripple marks, boulder bars, and scour holes that can still be seen along the river corridor. The volcanic activity did not just block the river, it also created entirely new landforms. Lava cascades froze mid-flow down steep side canyons, forming frozen waterfalls of black rock that look like petrified rivers of night. In a few locations, lava entered underground conduits and tubes, cooling into hollow tunnels that later collapsed or were exposed by erosion. One famous example is the remnants of lava falls. Not a waterfall of water, but a chaotic jumble of basalt blocks where lava once plunged over the rim and piled up in the riverbed, creating one of the most formidable rapids on the entire Colorado. Geologists have identified at least 17 major lava dams along a roughly 75-mile stretch of the inner canyon, with flows coming from at least 40 different vents. The eruptions were not continuous. They came in pulses, separated by thousands of years of quiet. Each pulse produced enough lava to dam the river multiple times, and each dam lasted anywhere from a few hundred to perhaps several thousand years before being completely removed by river erosion. Today, only fragments remain, enough to trace the outlines of the ancient lakes and understand how volcanic eruptions repeatedly altered the canyon's evolution. These dark volcanic rocks stand in stunning contrast to the bright sedimentary layers around them. Where red sandstone and limestone dominate the upper walls, the black basalt at river level creates a visual drama that photographers and river runners never tire of capturing. The contrast is not just aesthetic. It tells a story of two completely different earth processes colliding in one place. The slow, patient work of water carving downward for millions of years, interrupted by sudden, fiery outbursts from deep below the crust. Modern monitoring shows that the Uinkaret volcanic field is not extinct. Small cinder cones and lava flows are geologically very young, with the most recent activity dated to roughly 1,000 years ago. While no imminent eruption is expected, the region remains volcanically alive, reminding us that the forces that shape the canyon are still present beneath our feet. Float past one of those towering basalt columns, watch sunlight catch the glassy sheen on its faces, and feel the scale of what happened here. What looks like a quiet river canyon today was once the scene of repeated fire and water battles on a monumental scale. Those black scars are not scars at all. They are records of Earth's restless energy breaking through an ancient landscape and leaving its signature in stone. That fiery interruption in the canyon's long, watery history sets the stage for the next powerful force still at work today, the relentless river itself, carving deeper and wider with every passing season. Fact number 9 puts the spotlight on the single most powerful sculptor still shaping this landscape today: the Colorado River itself, a relentless living force that continues to carve the canyon deeper and wider with every passing season, even though most people only see it as a narrow green ribbon far below the rim. Stand at any overlook on a clear day and trace your eye down to where the river appears as a thin, twisting line of turquoise cutting through the dark inner gorge. From up here, it looks almost peaceful, a gentle thread winding between towering walls. But get closer, stand on the riverbank or ride a raft through one of the rapids, and the illusion shatters. The water moves with serious purpose. Average flow through the Grand Canyon ranges between 8,000 and 25,000 cubic feet per second, depending on the season and dam releases upstream. During spring snowmelt or controlled high-flow experiments, that number can spike much higher, sending walls of muddy water roaring downstream at speeds up to 12 miles per hour in the narrowest sections. This is not a lazy lowland river. The Colorado drops more than 2,000 feet in elevation from the eastern entrance of the park to the western exit, an average gradient of about 8 feet per mile, which is steep for a major river. That steepness gives the water tremendous energy. Every pound of sediment it carries acts like sandpaper. Every boulder it rolls along the bed grinds against the bedrock like a giant file. Geologists who have measured erosion rates in the canyon using cosmogenic nuclide dating and repeat surveys of riverbed profiles estimate that the river is still downcutting at an average of about 6 to 8 inches per 1,000 years in the inner gorge. Slow on a human timescale, but relentless on a geologic one. Over the past 6 million years, that amounts to roughly 1 vertical mile of rock removed, which is exactly the depth of the canyon today. The real work happens during floods. When heavy rain falls on the Colorado Plateau, or when Glen Canyon Dam releases a deliberate high pulse to mimic natural floods, the river transforms. Clear water turns chocolate brown as side canyons dump tons of mud, sand, and gravel into the main channel. Debris flows from narrow tributary canyons, triggered by summer thunderstorms, can deliver thousands of cubic yards of material in a matter of hours. These events build and destroy beaches, rearrange rapids, and expose fresh bedrock for the river to attack. Researchers from the United States Geological Survey have documented more than 500 debris flows entering the Colorado in the Grand Canyon since systematic monitoring began in the 1980s. Each one adds sediment that the river then sorts, transports, and eventually carries out toward the Gulf of California. Rapids are where the river shows its raw power most dramatically. There are more than 100 named rapids between Lee's Ferry and Diamond Creek, and about 10 of them are rated Class 8 to 10 on the Grand Canyon scale. Big, technical, boat-flipping drops with standing waves, holes, and lateral waves that can push a raft sideways into the wall. Lava Falls, Crystal, Hance, Hermit, each has its own personality shaped by the underlying geology. Some formed where lava flows constricted the channel. Others were huge boulders from rock falls created natural dams that the river had to punch through. The energy in these rapids is so concentrated that the river can move boulders weighing several tons during big floods, slowly but surely widening the canyon floor over millennia. Beyond erosion, the river also builds. During lower flows, it deposits sand and gravel in bars and beaches along the inside bends, places where rafters camp and hikers rest. These beaches are dynamic. They grow during floods when sediment supply is high, then slowly erode during steady low flows. Before the Glen Canyon Dam was completed in 1963, annual spring floods regularly replenished beaches with fresh sand. After the dam, sediment supply dropped sharply because most silt and sand settled in Lake Powell. Beaches shrank for decades until experimental high-flow releases began in the 1990s and 2000s. Those controlled floods, carefully timed and monitored, have helped rebuild hundreds of acres of beach habitat, proving that thoughtful management can partially restore natural processes even in a highly engineered system. The river's influence extends far beyond its banks. It controls groundwater levels in side canyons, feeds springs that emerge hundreds of feet up the walls, and creates the narrow riparian corridor where cottonwoods, willows, and cattails thrive in an otherwise arid landscape. Fish, amphibians, birds, and mammals all time their life cycles around the river's rhythm, spawning during spring rises, nesting when flows stabilize, migrating when water temperatures change. Scientists continue to study the river's behavior using stream gauges, sediment samplers, acoustic Doppler current profilers, and repeat bathymetric surveys from boats and drones. Data collected since the early 2000s show that while the dam has changed the timing and size of floods, the underlying geology and gradient still drive long-term incision. The canyon is not finished growing deeper. It is simply doing so at a pace we can measure with modern instruments, rather than eyewitness accounts. Sit on a beach at dusk, listen to the low roar of the next rapid around the bend, feel the cool mist rising off the water, and you understand. This river is not scenery. It is the living engine of the Grand Canyon. Patient, powerful, and still very much at work. Every grain of sand it carries downstream, every crack it widens in the bedrock, every beach it builds and then reshapes, is part of an ongoing story that began millions of years ago and will continue long after we are gone. That tireless carving action naturally draws our attention to the hidden water sources that keep life going, even where the main river cannot reach. The secret springs, seeps, and underground streams that quietly sustain pockets of green in the driest parts of this vast chasm. Fact number 10 draws our attention to the canyon's secret life support system. The hidden network of springs, seeps, and underground streams that quietly deliver water to places the main river cannot reach, creating tiny green islands of life in the middle of a vast desert chasm. You are hiking a narrow side canyon on a scorching July afternoon. The walls close in, the sun beats straight down, and every step kicks up fine dust that sticks to your lips. Then, without warning, you round a bend and hear it. The soft trickle of falling water. A thin ribbon of clear liquid slides down a sheer limestone cliff, pooling in a shallow basin before disappearing into cracks in the rock. Around that single seep grows a surprising patch of green. Maidenhair ferns with delicate black stems, scarlet monkeyflower nodding in the mist, crimson columbine swaying gently, even small clumps of moss clinging to wet stone. The air here feels 10 to 15 degrees cooler and noticeably more humid than it was just 50 feet back. This is one of the canyon's hanging gardens, isolated oases fed by groundwater that emerges hundreds of feet above the river. These springs and seeps exist because of the way the canyon's rock layers are stacked. The thick limestone formations, especially the Redwall and Muav, act like giant sponges when they are near the surface on the surrounding plateaus. Rain and snowmelt soak into porous rock on the Kaibab and Coconino plateaus, travel slowly downward through fractures and solution channels, and eventually hit impermeable layers deeper in the sequence, such as the Bright Angel Shale or the Supai Group shales. Unable to sink farther, the water is forced sideways along the contact between permeable and impermeable rock until it finds an exit, usually where the canyon has cut deep enough to intersect those flow paths. The result is a seep or spring emerging high on the wall, often in north or northeast-facing alcoves where shade keeps evaporation low. The National Park Service and United States Geological Survey have mapped more than 300 perennial water sources within the park boundaries. Some are tiny, a few gallons per minute dripping steadily, while others discharge several hundred gallons per minute and support year-round streams inside canyons like Havasu, Tapeats, and Thunder River. These waters are remarkably consistent in temperature, usually between 55 and 65 degrees Fahrenheit, because they come from deep aquifers insulated from surface extremes. That steady, cool flow creates microclimates where plants and animals can live in conditions far wetter and milder than the surrounding desert. The hanging gardens are biological hotspots. Botanists have documented more than 200 plant species growing in these wet pockets, including 20 or so that are found nowhere else outside the Grand Canyon region. Relict ferns and mosses that would normally thrive only at much higher elevations persist here because the constant moisture and shade mimic montane conditions. Orchids, small and unobtrusive, bloom in spring among the dripping walls. Several rare monkeyflower species hybridize in these isolated refuges, creating unique genetic combinations that scientists study to understand how plants adapt to extreme environments over long periods. Animal life clusters around these water sources too. California condors and peregrine falcons use the cliffs near springs as nesting ledges because the moisture supports prey populations, bats, rodents, and insects that would not survive without it. Canyon tree frogs breed in the shallow pools, their calls echoing after summer rains. Tarantulas, scorpions, and ringtail cats come to drink at night. Even bighorn sheep regularly trek long distances to reach known seeps during dry seasons, leaving well-worn trails along the walls. The water chemistry tells its own story. Many springs are slightly mineralized, carrying dissolved calcium, magnesium, and bicarbonate from the limestone they pass through. Some carry traces of uranium and other elements naturally present in the rock, but concentrations remain well below levels of concern for wildlife or occasional human contact. Researchers sample these waters regularly to monitor long-term changes in flow volume, temperature, and quality, data that help track how climate patterns and upstream groundwater use might affect the system. What makes these hidden waters especially precious is their vulnerability. Because they depend on recharge from distant plateaus, anything that reduces infiltration, prolonged drought, changes in vegetation cover, or increased evaporation from warming temperatures can cause flows to diminish or disappear. Several springs that were perennial in the early 20th century now flow only seasonally or have dried completely. Park scientists use repeat photography, flow measurements, and vegetation monitoring plots to document these shifts. The data show that while the system is resilient, many springs have persisted through centuries of natural dry spells. The current rate of regional warming and drying is pushing some to their limits faster than before. Stand beneath one of those dripping cliffs on a hot day. Mist brushes your face, ferns brush your legs, and the sound of water moving over stone feels almost musical after hours of silence and heat. What seemed like an impossible place to find life turns out to be sustained by a vast, unseen plumbing network carved through millions of years of layered rock. These seeps and springs are the canyon's quiet arteries, small in volume but immense in importance, keeping green refuges alive where the desert would otherwise win. That delicate web of hidden water naturally leads us to the next wonder: the extraordinary concentration of different living things packed into these narrow corridors and isolated pockets, and the careful efforts underway to protect them for the future. Fact number 11 brings us to one of the most remarkable aspects of this entire landscape: how such a narrow, rugged ribbon of canyons and side drainages manages to support an astonishing variety of living things, more species than you would expect in many much larger protected areas, and why keeping that diversity healthy has become one of the most important long-term challenges facing the park. From the rim down to the river, you cross through 5 major life zones in the space of a single vertical mile. That dramatic elevation change, combined with sharp differences in temperature, moisture, sun exposure, and soil type, creates dozens of distinct microhabitats packed close together. The result is a biological mosaic where plants and animals from very different ecological worlds live literally within sight of each other. Biologists have recorded more than 90 species of mammals, about 370 species of birds, more than 40 species of reptiles and amphibians, 17 species of fish native to the Colorado River system, and well over 1,700 species of vascular plants within the park boundaries. Among those numbers are dozens of species found nowhere else, or that reach the edge of their natural range here. Take the mammals first. At the rims you find familiar high desert residents: mule deer browsing on cliff rose and serviceberry, coyotes hunting rodents at dawn, black bears occasionally wandering down from higher plateaus in search of piñon nuts, Drop into the inner canyon and the list shifts. Ringtail cats prowl the riparian zones at night. Kit foxes hunt along sandy washes. And desert bighorn sheep, the classic canyon icon, navigate sheer rock faces with ease. The isolation created by the canyon walls has allowed some populations to develop slightly different traits from their counterparts on the surrounding plateaus. Subtle differences in coat color, body size, or behavior that reflect long-term adaptation to this unique vertical environment. Bird life is especially rich. More than 370 species have been documented, ranging from year-round residents to long-distance migrants that use the canyon as a critical stopover. California condors, as we mentioned earlier, now nest on remote ledges and soar on thermals rising from the hot inner gorge. Peregrine falcons, one of the fastest animals on Earth, hunt along the cliffs, reaching diving speeds well over 200 miles per hour. Southwestern willow flycatchers nest in dense thickets along the river, while zone-tailed hawks mimic turkey vultures to sneak up on prey. The vertical structure provides layered nesting and foraging opportunities. Cliff nesting raptors high up, cavity nesters in cottonwoods along the river, ground foragers in open washes. Reptiles and amphibians add another layer of diversity. 23 lizard species alone, from tiny side-blotched lizards that change color with temperature, to larger chuckwallas that graze on flowers and leaves. Several rattlesnake species occupy different elevations and habitats. Speckled rattlers and rocky outcrops. Grand Canyon rattlesnakes restricted to certain inner canyon drainages. Amphibians are fewer but fascinating. Canyon tree frogs that call explosively after summer rains. Red-spotted toads that breed in temporary pools. And the reintroduced Chiricahua leopard frog in some perennial side streams. The fish story is more complicated. Before Glen Canyon Dam, the Colorado River in the Grand Canyon supported 8 native species, 4 of which are now endangered: humpback chub, bony-tailed chub, razorback sucker, and flannelmouth sucker. These fish evolved under natural conditions of massive spring floods, heavy silt loads, and extreme temperature swings. The dam changed the river into a clearer, colder, more stable flow, which favored introduced trout over the natives. Recovery programs, including hatchery rearing, stocking, mechanical removal of non-natives, and high-flow experiments to rebuild spawning habitat, have helped stabilize humpback chub numbers in recent years, with several thousand adults now using the canyon reach. This biological richness does not happen by accident. The canyon's extreme topography creates barriers that limit gene flow between populations, allowing unique adaptations to develop over thousands of years. At the same time, the river corridor acts as a connective thread, allowing seasonal movement and dispersal. Side canyons with perennial water serve as refuges during dry periods. The result is a hotspot of endemism and diversity that stands out even among other southwestern protected areas. Protecting all of this is a complex, ongoing effort. The National Park Service works with scientists from universities, the United States Geological Survey, and tribal partners to monitor key species through camera traps, acoustic detectors, genetic sampling, and long-term vegetation plots. Invasive plants, especially tamarisk and Russian olive along the river, are removed by hand crews and targeted herbicide application to restore native willow and cottonwood habitat. Non-native fish are managed carefully to reduce predation and competition on natives. Climate change adds another layer. Warming temperatures push some species upward, while reduced snowpack on the plateaus threatens spring recharge to springs and seeps. Park managers use climate vulnerability assessments to prioritize actions, protecting the most at-risk springs, expanding riparian restoration, and maintaining ecological connectivity. What you see when you look across the canyon is not just beautiful scenery. It is a living, breathing system where thousands of species have found ways to coexist in close quarters under extraordinarily challenging conditions. Every hanging garden, every bighorn trail, every condor nest site is part of an intricate web that has taken millions of years to form and requires constant, thoughtful care to maintain. That extraordinary concentration of life leads us directly to the next layer of the canyon's story: the subtle but powerful earth movements that still occur beneath the surface, reminding us that this landscape remains geologically active and capable of change on human timescales. Fact number 12 reminds us that beneath the breathtaking stillness of these ancient cliffs, the ground itself is still quietly moving. Subtle but measurable earth shifts continue to shape the canyon in ways that connect this one landscape to much larger planetary forces. You are standing at the edge of the south rim on a calm morning. The air is clear, the views stretch for miles, and everything appears perfectly motionless. Yet sensitive instruments placed across the park have been recording tiny changes for decades, movements measured in millimeters per year that prove the Grand Canyon region remains geologically alive. These are not dramatic earthquakes that make headlines. They are the slow, steady breathing of the Earth's crust in response to deeper processes happening far below the surface. The most important of these processes is ongoing uplift of the Colorado Plateau. Roughly 6 to 8 million years ago, this entire region, a roughly 300,000 square mile block of relatively stable continental crust, began rising slowly but steadily. Average uplift rates across the plateau are estimated at about 1 to 2/100ths of an inch per year, though in some areas near the canyon, the figure is slightly higher. That may sound insignificant, but over millions of years, it adds up to thousands of feet of elevation gain. The reason the Grand Canyon is so deep today is not only because the Colorado River has cut downward. It is also because the land itself has been pushed upward, while the river has kept pace by eroding downward at roughly the same rate. This balance between uplift and incision is one of the classic examples in modern geology of how landscapes reach a kind of dynamic equilibrium. Researchers use a technique called apatite fission track thermochronology, combined with cosmogenic nuclide dating of river terraces, to reconstruct the history. Those studies, published in journals such as Earth and Planetary Science Letters and Geology over the past 20 years, show that uplift accelerated around 6 million years ago, roughly coinciding with the integration of the modern Colorado River system through the plateau. Before that time, the region had much gentler topography. Afterward, the land rose, while the river responded by carving the dramatic inner gorge we see today. Smaller-scale movements happen much closer to the surface. The canyon walls themselves are not perfectly stable. Freeze-thaw cycles in winter crack rock along joints, and summer heat expansion adds tiny stresses. Over time, these processes loosen slabs that eventually fall in rock slides or individual boulder drops. Park rangers and geologists document dozens of such events every year, most of them small, a few cubic yards of debris tumbling down a talus slope, but occasionally larger ones that close trails or alter river beaches. In 1983, for example, a significant rockfall from the North Rim sent thousands of tons of limestone crashing into the river corridor, temporarily damming a side stream and creating new rapids downstream. Seismic activity adds another layer. The Grand Canyon sits near the western edge of the Colorado Plateau, close to the transition zone where the crust begins to thin toward the Basin and Range Province to the west. Small earthquakes, magnitude 2 to 4, occur several times a year within 100 miles of the park. Most are too deep or too distant to be felt at the surface, but sensitive seismometers operated by the United States Geological Survey and regional networks pick them up regularly. These quakes are usually associated with normal faulting, the crust stretching and thinning, rather than the compressive forces that build mountain ranges. The faults responsible are mostly buried under younger sediments, but some have surface expressions in the form of small scarps or offset drainages visible on detailed geologic maps. One particularly interesting feature is the Toro Weep Fault, which runs roughly parallel to the river near Toro Weep Overlook on the North Rim. It has produced measurable offsets in young volcanic rocks and river terraces, indicating Holocene movement, activity within the last 11,700 years. While the fault is considered low hazard for large damaging earthquakes, its presence shows that tectonic stresses are still being released in small increments. Continuous GPS stations placed around the plateau edge detect millimeter-scale horizontal and vertical motions consistent with slow extension of the region. All of these processes, regional uplift, gradual fault slip, seasonal rockfalls, occasional small quakes, interact with the river's erosive power. When a fault moves even a little, it can steepen stream gradients or expose new bedrock, giving the river fresh material to carve. When large rockfalls enter the channel, they temporarily constrict flow and create rapids until the river works them down. The landscape is therefore a partnership between slow tectonic forces pushing upward and the river pulling downward, with gravity and weather adding constant small adjustments. Scientists monitor this dynamic system with an array of tools: permanent seismic stations, tilt meters, strain meters, repeat LiDAR surveys of canyon walls, and high-resolution satellite imagery that detects millimeter changes over time. Data from these networks help build models of future landscape evolution. How much deeper the canyon might become over the next million years, or how climate-driven changes in river flow could influence erosion rates. Stand at an overlook and feel the solid rock under your feet. It feels eternal, unchanging. Yet the instruments tell a different story. The ground is rising imperceptibly. Small faults are creeping. Rocks are loosening. And the entire system is responding to forces that reach deep into the planet's interior. The Grand Canyon is not a finished sculpture. It is a work in progress, one that moves on timescales both vast and surprisingly close to our own. That quiet but persistent tectonic pulse brings us to the final, most profound secret of all: what this one extraordinary place reveals about the larger history and future of our planet, and why its lessons matter far beyond these canyon walls. Fact number 13 brings everything together: the deepest, most far-reaching secret hidden inside these canyon walls. This single place serves as one of the clearest natural windows into the long story of our planet and offers quiet but powerful clues about where Earth, and life on it, might be headed in the centuries to come. You stand at the rim one last time as the sun drops low, painting the opposite cliffs in burning orange and deep purple. The immense space below you feels almost infinite. What you have seen over these 13 facts is not just a beautiful landscape. It is a carefully preserved record, a vertical timeline that stretches from the birth of ancient continents more than 1.8 billion years ago to the slow, ongoing changes happening right now. Few places on Earth let you walk through such a complete, continuous slice of deep time in one breathtaking view. That alone makes the Grand Canyon exceptional. But its real power lies in what it teaches us about patterns that operate on planetary scales. Start at the bottom, with those dark Vishnu schist and Zoroaster granite rocks, remnants of volcanic island chains and colliding landmasses that formed part of the supercontinent Rodinia long before complex life appeared. Move upward across the billion-year gap of the Great Unconformity, and you cross into the Cambrian explosion, the sudden burst of diverse animal life recorded in trilobite trails and early burrows. Higher still, the layers show ancient tropical seas teeming with brachiopods and crinoids, vast coastal deserts with reptile trackways, swampy floodplains where early forests left their marks, and finally, the shallow Permian Ocean that left the Kaibab limestone capping the rim. Each layer is a snapshot of a dramatically different world: different climate, different geography, different chemistry of the oceans and atmosphere. Those changes were driven by the same fundamental forces that still operate today: plate tectonics rearranging continents, volcanic outgassing altering carbon dioxide levels, orbital cycles triggering ice ages, massive weathering events drawing down greenhouse gases. The Grand Canyon preserves unusually clear evidence of several of these cycles in one location. The repeated rise and fall of seas recorded in the Paleozoic strata mirror global sea level changes linked to the assembly and breakup of supercontinents. The Great Unconformity itself appears across much of North America and parts of other continents, a worldwide signal of massive erosion, possibly tied to the breakup of Rodinia and the snowball Earth glaciations that followed. Studying this one canyon helps scientists test and refine models of how those ancient global events unfolded. Now look forward. The same processes that shaped the canyon are still active, just slower and more subtle in human lifetimes. Regional uplift continues at a few hundredths of an inch per year. The Colorado River keeps incising at roughly 6 to 8 inches per thousand years. Small faults creep, rockfalls happen, springs respond to distant recharge. Add the rapid changes humans are introducing: warming temperatures, shifting precipitation patterns, altered river flows from dams, and the canyon becomes a living laboratory for understanding how landscapes and ecosystems respond to combined natural and human-driven stress. Scientists from dozens of institutions use the Grand Canyon as a natural experiment site. Long-term monitoring of springs shows how groundwater systems react to drought and warming. Vegetation plots track upward shifts in plant communities as average temperatures rise. River sediment studies measure how controlled floods rebuild beaches and spawning habitat in a dam system. Seismic and GPS networks watch for tectonic signals that could influence future incision rates. All of this data feeds into broader climate and Earth system models, helping predict how other arid regions, mountain ranges, and river systems might evolve under similar pressures. What emerges from those studies is both sobering and hopeful. The canyon has endured enormous changes before: seas advancing and retreating multiple times, supercontinents forming and splitting, ice ages coming and going. And life has always found ways to adapt. Hanging gardens persisted through dry spells, native fish survived massive natural floods, bighorn sheep navigated shifting climates. Yet the current pace of change is faster than most previous natural shifts recorded in the rock layers. That speed challenges the resilience built over millions of years. At the same time, the canyon demonstrates how thoughtful human intervention can help. Controlled high-flow experiments from Glen Canyon Dam have rebuilt hundreds of acres of riparian habitat. Invasive species removal has restored native plant communities. Condor reintroduction has brought one of the continent's most endangered birds back from the brink. These successes show that when we understand the natural rhythms preserved here, we can work with them rather than against them. So when you look into the Grand Canyon, you are not just seeing beautiful rock and river. You are seeing a four-dimensional story: past worlds stacked vertically, present processes moving horizontally, future possibilities written in subtle shifts of temperature, water, and stone. This place holds lessons about resilience, about the deep interconnectedness of Earth systems, about how small changes at one scale ripple across continents and eons. It reminds us that we are temporary visitors on a planet that has been writing and rewriting its own history for billions of years, and that the choices we make now will become part of the next layers future geologists will study. The Grand Canyon is more than a wonder. It is evidence, quiet, immense, undeniable, that Earth is a dynamic, living system still in the middle of its story. And by paying close attention to what it has already recorded, we gain the clearest possible view of where that story might lead next. Now you have seen all 13 secrets laid open, from billion-year gaps in the rock record to the hidden springs that keep life going. From ancient human footprints to the slow tectonic pulse still lifting the land. From the river's patient carving to the lessons this one landscape offers about our shared planetary future. Which of these hidden wonders surprised you the most? Drop it in the comments below. I read every one and love hearing what stayed with you. If this journey through the Grand Canyon moved you, share it with someone who needs to see beyond the postcards. Thank you for staying with me all the way to the end. Take care of yourselves, treat this irreplaceable place with respect, and I hope to meet you again soon on another deep dive into the wonders our planet still holds. Until next time.